Okay. Uh, Good evening, everyone. So, welcome to this live session on 24/11/2025. Okay. So, in this live session, what we will do is before we getting into the this week content. Okay. So, what we will do is we will solve a problem on Bode plot. Just as a recap of previous week from the week 7, then we will do the revisiting of the content, and if time permits, we'll solve one or two problems. Okay. So first of all, Bode plot, which is part of the frequency response. So basically, we use the Bode plot to draw the frequency response of a open loop transfer function. So that is nothing but so g of s, uh, let's say gc of s, which is controller transfer function, and Planck transfer function is g of s. So what we will do is we will find the transfer function. Okay, so the open loop transfer function in the Bode plot. Okay, so we'll find its transfer function value along the j omega axis. So then it would become gc of j omega, g of j omega. Okay, so in the Bode plot, we draw two plots. So one is the magnitude plot. So the other one is the phase plot. Okay, so one is magnitude plot, that is 20 log mod z c of j omega g of j omega. Then another is phase plot. So angle gc of j omega to j of j omega. Okay, so on y-axis we have one side magnitude. Okay, so which we also called as log magnitude. So the other one is phase magnitude. On the x-axis we'll have the frequency. So frequency radians per second. Okay, so we vary these frequencies. So starting from 0 to up to maximum. So in the orders of 10 we take. So 0.1, 1, 10, 100, so etc. So we will draw these two plots. One plot is called as the magnitude plot, other plot is called as the phase plot. This is what basically the Bode plot indicates. Okay, so first we will see what are the major things in the Bode plot. Okay, so let me separate this into two. So in one we have magnitude as well as the phase plot. Okay, so this is omega frequency. Okay, so here we have the open loop transfer function g in decibels, and another one is phase angle phi. Okay, so now let's say the so the modal plots. Let's say we have something like this magnitude plot, and phase plot also we have something like this. Okay, so here what we do is, so we will check where we have this zero magnitude line. Okay, and here also we will check something called as minus 180 degree the line. Okay, here it is zero magnitude, and here minus 180. Okay, so here what we do is, so wherever we have, we consider this coordinate. So the coordinate is nothing but minus 180 on y-axis, and x-axis we call that is as uh, omega pc, phase crossover frequency. That means that is somewhere here. Okay, yeah. So that is somewhere here. This is the omega PC. So phase crossover frequency. Okay. So now we by taking this coordinate and extrapolating that to the magnitude magnitude plot. Okay. So now you wanted to check. Okay. So that is intersecting with the magnitude plot here, which is below the 0 dB axis. Okay. So we have this much uh, gap we have. Okay. So this we call it is as a gain margin. Call that is as a gain margin. Let's say if that value is let's say if that value is some 10. Okay. So minus 10. Okay. So we call the gain margin as 10 dB. Okay. Similarly, in case if that comes in the above the 0 dB line, so we take gain margin as minus 10 dB. Okay, so now here we are defining three things. So two things. So one is the phase crossover frequency. So that is the frequency at which this minus 180 degree line cutting this phase angle curve. Okay, then we take that phase crossover frequency and extrapolate it to the magnitude curve. So there we have this called as the gain margin. Gain margin is something that how much the magnitude plot deviated went below or above the 0 dB line. Okay, that is called as the gain margin. Okay, so this is one part. The other part is same curves we can consider. Okay, so we have x-axis is omega. So similar way, that is magnitude, the g, dB, angle is g. Okay, so phase angle. So similarly, again, let's say we have these two plots, magnitude as well as the phase plot. Here, what we do is here we will consider in the reverse way. Now we will do. So this is the 0 dB line. We will check where this 0 dB line is intersecting with the magnitude plot. Okay, let's say that is 0 on the y-axis. Here we say that is omega gc, which is nothing but the gain crossover frequency. Gain crossover frequency. Okay, so here we have phase crossover, here we have gain crossover frequency. Now at this, the gain crossover frequency is nothing but this one on the x-axis. Okay, now at this point, okay, if we uh, uh, extend that to the phase angle curve, so that is this point. If we extend that to the phase angle curve, right, and we will see, we'll consider this 180 degree line also. Okay, we'll consider this 180 degree line somewhere here. Let's see. Okay, minus 180. So now we will see from minus 180 how much the angle is deviated. Okay, so that deviation we call it is as the phase margin. Call it is as a phase margin. So that we can say that is P plus 180. Okay, where P is nothing but, so the amount it is deviated. The amount it is deviated. So let's say if it is some minus 200. Okay, so my phase margin is going to be minus 200. Okay, so plus 180, it is going to be some minus 20 dB. Sorry, not dB, 20 degrees. Okay, so that is the phase margin. Similarly, we can have the other side also. If that minus 180 is coming down, okay, so you can have the other side also. So you'll have your phase margin here. Okay, so that we will say it is as a depends upon whether that uh, so the phase plot is above or below the 180 degree. So how much it is deviated. Okay, so that we call it is as a phase margin. One is positive, one side is positive, other side is negative. Okay, so totally here we got four terms. So the gain margin, phase crossover frequency, and phase margin, gain crossover frequency. Is this clear? Any doubt or query?
Another.
Yeah. So these two are very important, gain margin and phase margin. Okay. So using these two, we will decide the system stability. Okay. So generally what we do is if these two are positive, okay. So if gain margin comma phase margin positive, okay. So we say that system is stable. Okay, if gain margin and phase margin are negative, we say system is unstable. So in case of the poles positive and poles behavior with respect to the j omega axis, whether they are on the left side or right side, here in the frequency domain we decide the stability based upon the sign of the signs of the gain positive and gain margin and phase margin. Okay, so we say a system is stable or unstable. Hope this is clear. So what we will do is we will solve one problem and then we will getting into this week content. Okay, so let me write the question. Okay, so question is let me use another pen. So sketch the Bode plot. Okay, so for the following, so transfer function and determine the system gain. Okay, system gain K. So for gain crossover frequency to be 5 radian per second. Okay, so we need to first draw the Bode plot and we need to determine for which value of system gain K. Okay, so the gain crossover frequency will be 5 radian per second. So the open loop transfer function is given as K S square divided by, so 1 plus 0.02 multiplied 1 plus 0.02 S. Okay, this is our open loop transfer function. Okay, so first now let us take the first step, drawing the Bode plot. In drawing the Bode plot, what we do is, so as a step one, okay. So first, let us write this g of s as k s square by 1 plus 0.2 s multiplied 1 plus 0.02 s. Okay, so we can write this one as some k s square by 1 plus st1. We are trying to identifying the time constants. 1 plus st2. Okay, so then substitute to s equal to j omega. So we get g of j omega as k j omega square divided by 1 plus 0.2 j omega 1 plus 0.02 j omega. Okay, so now let us this is first step. Okay, so let's take here k is equal to 1. Okay, so take k is equal to 1. If we take k is equal to 1, so let me write here. Okay, so we'll be having our g of j omega as, okay, so j omega whole square by, so 1 plus 0.2 j omega divided by 1 plus 0.02 j omega. Okay, so that is step 1. Now step 2, what we do is we form a table. Okay, we form a table. Let's say serial number. So we take individual terms, then we identify corner frequencies. Okay, so which are radians per second. Okay, then we find the slope at each corner frequency in radians per second. Then we also find the change in slope, so which is also radian per second. Okay, so we find this table. So we find this table. Based upon this table, okay, so we draw the Bode plot. Now you can check the transfer function. We have total 3 terms. So we have 3 terms. So the terms are j omega whole square. So the other one is 1 by 1 plus 0.2 omega, right? So the other one is 1 by 1 plus 0.02 omega. Okay, so we'll find the corner frequencies. Here j omega square will not having any corner frequency. Okay, the other term, the corner frequency here is, so 1 by 0.2, because 0.2 is the time. Okay, so the frequency is inverse of the time. Similarly, omega c2 is 1 by 0.02, so that is 50. These are the corner frequencies at 5 and 50. Now we will find the slope. Okay, j omega square means that is plus 40. Okay, so because it is in the numerator, so each term will each s will add up to a plus 20 dB per decade if it is numerator. If it is denominator, it will be minus 20 dB per decade. Here it is numerator twice, so plus 40. Then this is minus 20, so because it is in the denominator, this is also minus 20. Now we shall find the change in the slope. So here previous to this 40 there are no other terms, so there is no slope here. Then the second slope is, we take this 40. Okay, then we add the next slope. Okay, so that means we take 40 here, we will add this one here. Okay, so that will be 20. Okay, next what we do is we take this 20 here and we will add this one here. Okay, so that means we'll take 20 here plus we'll add minus 20 over there, that is 0. Okay, so are there any doubt here in finding this table?
No, sir.
Yeah, so based upon this table, okay, so we will write our Bode plot. So before going to that, okay, so then step 3. Okay, so in step 3 what we do is, so the lowest frequency here is the so we will lowest frequency here is 5. Okay, so we will choose another frequency which is very far from 5. Okay, so let's say choose a lower frequency, low frequency, so such that you will be choosing lower frequency as omega L, which is less than omega C1. Okay, so here omega C1, you know already, that is the 5 radians per second. Okay, so now you choose your, generally we choose let omega L is mostly what we do is we choose 10 times less. Okay, so that means like 10% of 5. Okay, so this will be almost equivalent to 0.5 radians per second. Okay, so next, so that is our omega L. Okay, next what we do is we calculate at omega L, we calculate this magnitude. Okay, so now first we will consider what is this omega. So that is mod z of j omega, that is in dB. So which is nothing but 20 log mod z of j omega. dB means 20 log. So now yet omega L is equal to 20 radians. Sorry, omega L is 0.5 radians per second. So what is my A value? A value is going to be 20 log mod j omega square up to that point. Okay, because up to omega c1, okay, so which term is dominating? The term dominating is j omega square. So that's why we took that only as g of j omega. Okay, so now substitute it. So 20 log, this is going to be omega square. So 20 log, so this is going to be 0.5 square. Okay, if we calculate it, okay, so we will get minus 12 dB. Okay, so that is at omega L. Okay, next, so we will calculate at omega C1, which is nothing but 5 radians per second. So what is the A value? That is nothing but 20 log. So again same omega square. So that becomes 20 log 5 whole square. Okay, so this we will get it is as 28 dB. 28 dB. Okay, so this is the first step. Okay, first step is, so here we have chosen, we got our corner frequencies as 5 and 50. Then we will choose some omega L. Okay, so which is almost 10% of that omega C1. Then starting with omega L, we'll find the magnitude. Then at omega C1, we'll find the magnitude. Okay, that is step 3. Next, step 4. Okay, so what we do is now add to omega C1. Okay, so what do we have? So A is 20 log omega square, correct? So that is nothing but 20 log 5 square. This is 28 dB, correct? Next, add to omega equal to omega C2. Okay, so omega C2 is how much? Omega C2 is 50. Okay, now we are interested to find what is the A value here. Okay, so the A value here is nothing but you are trying to finding between 2 points. So this is omega C1, this is omega C2. Okay, so then we find the A value as in the same form y is equal to mx plus c. So add to omega, A value at omega is equal to omega C1 plus the slope from omega C1 to omega C2. Okay, so multiplied log omega C2 by log omega C1. This is how we will calculate the A value at next point. Okay, so this is the same formula applicable for any other omega c's. Okay, so we calculate like, so here we got omega C1. This one is 28, the first term, plus the slope is 20. Okay, log 50 by 5. By the way, how this is 20? This one is omega C1 to omega C2 from the table. Okay, that is the slope, starting slope at omega C1. Okay, so that's why I took 20 here. Okay, so then when you do the calculations, so this one you will get 48. The units are dB. Okay, so that is the value of this magnitude at omega is equal to omega C2, which is 50. Okay, next. So next is step 5. Okay, so now what we do is, so we've already reached omega C2. Omega C2 is the last one in our table. Okay, so but we have to do the calculations here for all the omegas. Okay, so now what we do is, after omega C2, we choose a high frequency value, which is a high frequency such that omega H, which is far less than omega C2. Okay, here what we do is, so we choose, we can choose any value. Okay, so generally what we do is, we choose some 2 times for omega C2 or the ending omega. So now at omega is equal to omega H, which is nothing but 100 radians per second. So we wanted to calculate the magnitude. So we calculate the magnitude in the similar way. A value at omega is equal to omega C2 plus again slope from omega C2 to omega H. Okay, so that's the last slope in our table. So log omega H by omega C2. Okay, so that slope is how much? This one, 0. Okay, so now we will substitute. So this we already know, at value omega is equal to omega C2, that is already 48, plus the slope is 0, multiplied log 100 by 50. Okay, so this is again equivalent to 48 dB. Okay, so now starting with omega L, we have started at omega L, then omega C1. Okay, omega L, then omega C1, then omega C2, then omega H. So for this entire sequence, so we calculated all its magnitude values. Okay, is there any doubt in this? Any doubt or queries? Yeah.
No, sir.
Yeah. So now we got all our magnitude values. Now what we will do is, similar way we'll find the phase values also. Okay, so to draw the phase plot, so what we do is, using our transfer function. Okay, so what is our transfer function we have? So transfer function is g of j omega, where k is equal to 1. So j omega square divided by 1 plus 0.2 j omega 1 plus 0.02 j omega. Okay, so for this, so we are finding the phase. Okay, so the phase is nothing but, so g of j omega, so which is nothing but the numerator. So that is that is related to s square. S square means 90 plus 90. Okay, so minus tan inverse, the first term is 0.2 omega, minus tan inverse 0.02 omega. So this is the phase. So this is the phase. Okay, so now what we do is, just like the previous case, okay, we form this table. So serial number, omega radians per second. Okay, so tan inverse 0.2 omega. So the other one is tan inverse 0.02 omega, and last one is pi. Okay, so now for all these same omegas, okay, so we will calculate. So we have 0.5, 1, 5, 10, 50, 100. Okay. So let's say 1, 2, 3, 4, 5, 6. Okay. So these values you'll get as 5.7, 11.3, 45, 63.4. If you do the calculations, 84, 87.1. This one is 0.6, 1.1, then 5.7, 11.3, 45, 63.4. Okay, so the values you get corresponding angles as 174, 168, 130, 106, 50, and 30. Okay, so now we have the phase plot needed data, and we have the magnitude expressions, magnitude values. Okay, so now let us plot, okay, the magnitude plot and phase plot. Okay, so let's plot magnitude plot here. Let's say this is magnitude plot, and in the same way the phase plot. Okay. Okay, so the magnitude plot is 20 log mod g of j omega. Phase plot is angle g of j omega. Okay, so so on the x-axis we'll be taking 0.1, so 0.5, 1, 5, 50, 100, let's say. Okay, so here also in the same way. Okay, so almost to 0.1, 0.5, 1, 5, 50, 100. Okay, so this is omega. Okay, so now look at the previous values. Okay, so we have done the calculations. So at omega L, this is omega L, omega C1, omega C2, this is omega H. Okay, so let me write it down. So this is omega C1, omega L, sorry, omega L, omega C1, omega C2, omega H, correct? Omega L, omega C1, omega C2, omega H. Okay, now look at the values, the values which we have calculated. Okay, so at omega C1, okay, so at omega L, okay, we have calculated that as 12 MB. Okay, so the magnitude. Okay, I'll write them first. Then at 5, that is omega C1, we calculated omega C1, we calculated that as 50. Then at 28, then at 50, we calculated it as 48. Okay, so that then that continues for 100 also. Okay, let me put these values, you'll understand. This we have calculated as minus 12, this is 28, this is 48. Okay, so these are the points. Okay, so if you want you can check them at omega L. Okay, so at omega L the value is minus 12. At omega C1 the value is 28. At omega C2 the value is 48. At 100 the value is again 48. Okay, so these are the values omega L, uh, sorry, omega L, omega C2, Okay, this is omega. I'm sorry, this is omega C1 5. Okay, so this one and omega 100. So that is again 48. Now, how do you connect them? So you can start connecting them like this. So this is one point, this is another point. Okay, so then from here you'll have next point here, right? Then from here continues. Okay, so this is the way. Okay, so this is how it goes. This is the Bode plot. Okay, then next, so we have this table as well. Okay, so the this table starts at 174 and ends at 30. Okay, so the values are like this. Okay, so at omega L the value is 30. Okay, then the at omega C the value is 130. Somewhere here, let's say. Okay, then omega C2 the value is 50. Okay, oh, I'm sorry, at omega L the value is 174. Okay, last at omega H the value is 30. Okay, so omega L the value is 174. Next the value is 130 from this table only. Okay, then the value is 50, then it is 30. Okay, so these are the points. Okay, these are the points, so you can connect them now. You can connect them like this. Yeah, so this is the magnitude plot. Okay, this is the phase plot. So magnitude plot and phase plot. Is this clear? Are there any doubts?
No, sir.
Yeah, so for drawing the Bode plot. Okay, so now look at our first question. Okay, so we have completed this part. Okay, drawing the Bode plot. Now, so we have to answer this question: what is the value of gain k for which we get our gain crossover frequency as 5 radians per second? Okay, so basically, what is the gain crossover frequency? Gain crossover frequency is the this one. So in the left side, right side, you have gain crossover frequency is when this phase will be equivalent to 180 degrees. Okay, so the phase crossover frequency. Okay, so we have to find phase crossover frequency and the uh, when the phase is 180 degrees. Okay, so gain crossover frequency is the other way. Okay, so phase crossover frequency is the other way, where the gain will be I'm sorry, gain crossover frequency is uh, when the uh, gain is 0 degrees. Okay, phase crossover frequency is the other way. Okay, so now let's do the calculation. Okay, so as per the question, gain crossover frequency is okay, gain crossover frequency here. So mod g of j omega, here the frequency will be equal to gc. That should be equivalent to 1. So that means, so 20 log, okay, 20 log, So that is equivalent to mod g of j omega gc. That is equal to 0. Okay. So from here we can, if we observe there, okay, when that will be 0, so then omega gc is equivalent to 1 radians per second. Okay, so this is for the case when k is equal to 1. Okay, now what is our question? So we want our omega gc will be equivalent to 2. Okay, so 5 radians per second. Okay, so g of j omega gc, that is equivalent to 1. Okay, so now at 5 radians per seconds means what? 5 radians, 5 magnet, the 5 radians per seconds means that is this one. So at this level, the magnitude is 28. Okay, so we can write this one as, okay, so that means the magnitude plot, okay, okay, should magnitude plot should down by, okay, 28 dB. Okay, so that means what? So 20 log k is equivalent to minus 20. It has to come down. Okay, so then k is equivalent to what? 10 power, because this is log k base 10. 10 power minus 20 by 20. Okay, so that is equivalent to 0.0398. Okay, so for that value of k, we will get our gain crossover frequency as 5. Okay, so that is
Sir,
the
can you
expression.
explain this again,
Yeah.
sir?
Yes,
No,
yes.
no, I didn't understand this. 20 log k equal to minus 28.
So grain crossover frequency 5. Okay, so this one, correct?
Yes, sir.
We wanted to make gain crossover frequency as 5.
Oh,
Okay,
okay. Yes, sir.
so what should I do? I need to bring, that is 28. Okay, we need to
Okay.
move that to 28 down. Then only this point will go to 0.
Oh, yes, sir.
Yeah, so that's why 20 log k is equal to minus 28.
Okay.
Yeah, so then we calculate the k. Okay, so here the point is, you can see again here. So the phase margin is phase margin and gain margin. Okay, so they are related to phase crossover frequency and gain crossover frequency. Okay, so we'll see the next question. So in the same way, let's say the second question. So the open loop transfer function is given. Okay, so g of s equivalent to 20 by s into s plus 1 s plus 5. Okay, so here the question is calculate, so calculate gain margin, uh, gain margin, phase crossover frequency, phase margin, gain crossover frequency. Okay, so using the Bode plot. Okay, so I'll write these steps directly. Okay, so let us solve this one quickly. So in step 1, what we do, z of j omega. Okay, so that is 4 by j omega 1 plus j omega. This is 1 plus 0.2 j omega. Okay, so what we are trying to doing is we are trying to writing the denominator roots as 1 plus st format. Okay, so that's why here we have 0.2 omega. Okay, so we are taking the 5 common. So then 5 and 20, so it got resulted in 4. Okay, so now we are writing this table. Okay, so let's say we'll quickly write this table also. So we have term here. So corner frequency. Okay, here we have slope dB per decade, and here change in the slope. Yeah, change in the slope. Okay, so let's say here serial number. So how many terms we have? 1, 2, 3, 3 terms we have. So first one is omega, second one is 1 by 1 plus j omega, third one is 1 by 1 plus 0.2 j omega. Okay, so here omega c1 is 1 by 1, that is 1. Omega c2 is 1 by 0.2, that is 5. Same 5 you will get. Okay, here the slope is minus 20 because 1 by s. Okay, there is no change in the slope because there are no other terms. Here the slope is minus 20 because the pole is, it is the pole. Okay, now change in the slope is minus 20 plus minus 20. How do we do this? This first minus 20 is this, then second minus 20 is this. Okay, so what is the slope? Minus 40. Similarly, next one is, this is also minus 20 because it is a pole. So what is the resulting? Minus 40 plus minus 20, which is minus 60. Again, same thing. We take this one here and this one here, minus 60. Is this clear?
Yes, sir.
Uh, yeah, that is how we will find the change in the slope. Okay, so this is our second step. Okay, let's say third step, what we do, we choose omega L, lowest frequency compared to omega C1. Okay, so we choose, let's say, omega L as 0.1. Generally, we take 10% of this omega C1. Okay, so what is the first one? At omega is equal to omega L. So A is equal to 20 log 4 by omega, the first one. Okay, so we do the calculation. So that is 20 log 4 by 0.1. Okay, so we'll get 32 dB. Okay, next at omega is equal to omega C1. Okay, so A is equal to 20 log 4 by omega C1 is 1. This one. Okay, so that is equivalent to 12 dB. Okay, next, that is step 3. Next, step 4. Okay, so at omega is equal to omega C2, which is nothing but omega C2 is 5. Okay, so at this value of A is what? Okay, so A at omega is equal to omega C1 plus slope change from omega C1 to omega C2 multiplied log omega C2 by omega C1. So what is it? So this value is 12 plus slope change is minus 40, this minus 40. Okay, so log 5 by 1. Okay, you get what? Minus, sorry, this is 12 and this is minus 28. You get minus 16 dB. Okay, next, fifth one is you choose some highest frequency omega h, which is greater than omega c2. Okay, so generally what we do is we take, so 2 times omega c2. So which is nothing but omega c2 is already 5. So this will be 2 times of 5 is 10. Okay, then we calculate A here. This is also same. So A at omega is equal to omega C2 plus slope from omega C2 to omega H multiplied log omega H by omega C2. Okay, so first value is minus 60, which we know already. Okay, no, not minus 60. That is this one, minus 16. This goes here. Okay, because this is this. Okay, so plus minus 60 multiplied 10 by 5. Okay, so if you calculate it, you will be getting minus 34 dB. Okay, so now let's plot this. Okay, let's plot this. Okay, so omega L is 0.1 and omega C1 is 1. Okay, then omega C2 is 5. Then omega H is 100, 10. Okay, so now let's identify the values at omega L. What is the value? At omega L is 32, the next is 12, next is 16, next is minus 34. Okay, so omega L, that is 32. Okay, at omega 1, that is 12. It is like this. Okay, then omega C2 minus 16, this is minus 16, then omega H is minus 40. Okay, so minus 6 is here, minus 40 is here. Okay, so these are the points. So first point, second point, third point, fourth point. These are the magnitudes. So if you connect them now, okay, so these are the values. So this will be like minus 20 dB per decade. Okay, so this one. This will be minus 40 dB per decade, the slope. Then this will be minus 60 dB per decade. Okay, now first we need to find the phase crossover frequency. So what is phase crossover frequency? So the phase crossover frequency is when the gain is 0. So where is the gain? This one. This is 0 dB line. Okay, when it is becoming 0, so that is becoming 0 at this point. Okay, so this is nothing but omega PC. Okay, so the gain phase crossover frequency. Okay, so the phase crossover frequency is when the gain becomes 0. Okay, here you can write that is as, since that is in between 1 and 5, so that is approximately equivalent to 2 radians per second. Okay, so that is the expression. Is this clear? Any doubt? Okay, similarly we can find,
Sir,
we
this
can
is gain
find,
crossover frequency, no, sir.
sorry.
This one is gain crossover frequency, no, sir.
Yeah, this is gain crossover frequency. Okay, so next, similarly we can find the phase crossover frequency. So what we have is g of j omega as 4 by, okay, so j omega 1 plus j omega 1 plus j 0.2 j omega. Okay, so here the phi would be like So angle g of j omega is okay minus 90 because j omega in the denominator. So minus tan inverse omega. So minus tan inverse 0.22 omega. Okay. Similarly, if you do the calculations, okay. So for same values of omega, so omega, so you can have these values. Okay, tan inverse omega, tan inverse 0.22 omega. Okay, then finally you have phi is g of j omega. Okay, so you can take different values 0.1, 0.5, 1, 5, 10, 50, 100. Okay, so if you calculate them, so you'll be getting this one as 5.7, 26.56, 45, 78, 84, 88, 89. Okay, so these are approximated values. Okay, similarly this one is 1, 5, 11, 45, 63, 84, 87. Okay, so final is minus 97, minus 122, minus 146, minus 214, minus 238, minus 263, minus 267. Okay, so these are all approximated values, not exact values. So now you can plot them here. Okay, so these are all our minus values. These are all our minus values. So omega, so this is 0.1, so 0.5, 1, 5, 10, 100, let's see. Okay, so this is angle C of z omega. Okay, so you can write them at 0.1 you're getting minus 97, at my 0.5 it is minus 122, at 1 it is minus 146. Okay, so then at 5 it is 214, minus at 100 it is close to 267. Okay, so uh, these are the points. Okay, so you can connect them from here. Okay, so if you connect them one by one. Okay, so now somewhere here you'll be having your minus 180 line. Okay, minus 180 line. So you should see at which point that is intersecting. Yeah, this one. Okay, so this one. So this will be like omega PC 2.2 radians per second. So when the angle becomes equivalent to uh, 2.2 radians per second. Okay, so now what you can do is, okay, so you have to calculate the phase margin and gain margin. Okay, so those are the two expressions. So then third one is gain margin. Okay, so gain margin, how do we generally gain margin? We represent with Kz. Okay, so how do we calculate so that we can take it like this? 20 log 1 by, okay, so mod g of j omega pc. Okay, so that is 20 log. Okay, so 1 by, so mod, we have 20 numerator by root over 1 plus 2 square. Okay, 20 plus 25 plus 2 square, because omega bc is 2. Okay, so that is 2 dB. Okay, similarly, next we can calculate the phase margin as, so phase margin gamma. So that we will calculate as 180 plus, so the pi gc. Okay, so the gain crossover frequency. So first, what is pi gc? 180 plus what is pi gc minus 20 plus tan inverse, wherever there is a omega, substitute gc minus, okay, this also has to be minus tan inverse. Okay, so 0.2 omega gc. Okay, so here what is pi gc? We got pi gc is 2.25. Okay, so you can substitute here. So this will become plus 90 minus tan inverse. So that is 2.2 minus tan inverse 0.2 2.2. Okay, if you do the calculations, so you will get 5 degrees. So which is a positive value. Okay, this is also a positive value. Okay, so now what are the observations? Yeah, by the way, just a minute. So this has to be pi gc, and this has to be pi pc. Is this clear? Is this clear?
Yes, sir.
You can see here. So the phase crossover is the frequency at which the gain margin is, this is the frequency when we are looking for the expression, this one, 0 dB. Okay, so that is how it goes. To find the gain margin, we will check the phase crossover frequency. To calculate the phase margin, we need gain crossover frequency. Okay. Yeah. So now here you could see the observations. Okay, so first one here, the phase margin and gain margin. Okay, so both are positives. Both are positives. So second observation is, if you see the magnitude part, okay, so that is below the 0 dB line. Okay, and the phase plot, so below the 0 dB line at omega bc, and phase plot that is above minus 180 at omega gc. Okay, so hence, so system is stable system in the closed loop system. Closed loop system is stable. Okay, so now that we know how to draw the Bode plot and able to identify phase margin, gain margin, and for system stability, the both has to be positive, and if they both are negative, the system becomes unstable. Okay, so now how can we use this information, the information of phase margin and gain margin? Okay, and again check the design specifications. In last week we saw this design of compensators based on the root locus. Now for the same systems, right, can we design the compensators based upon the Bode plot or frequency response. Okay, so that is this big content. Can you do you have any doubts? Yes, yes.
Point one, what have you written? Like
Which one?
here, kg, comma.
Gamma. Gamma is phase matching.
Okay, sir.
Yeah, so this is phase matching and this is gain matching. We represent with these terms. Okay, so now let's go to that part. Okay, so let's start with this. This is what we saw in the previous week. Okay, so we saw the compensator designs, right? So which will help us to meet the design specifications of the system. Last week we saw based upon the root locus. That means, roughly speaking, so the design specifications are directly represents in terms of the overshoot, settling time, right? So first what we do, given overshoot and settling time, we convert them into dominant poles location. Let me, yeah, so dominant poles location. Then we have, then we from the dominant poles location, first what we do, we will draw the root locus for the given system. Okay. Then we will locate these poles, dominant poles. Okay. So let's say if the root locus is like this, we'll check the dominant poles, uh, whether they are on the root locus or not. Okay. So if they are not on the root locus, what we need to do is we need to reshape the root locus, okay, in such a way that it must pass through these dominant poles. Then we say that, okay, we met the design specifications. Okay, so that's what we saw. Now in the similar way, using this frequency domain, okay, so here our design requirements are maybe indirectly specified. So whereas previously they are in terms of the overshoot settling time, now they will be indirectly specified with phase margin and gain margin and other factors like resonant peak, bandwidth, etc. Okay. So now what we do in the similar way, okay, so using these design specifications, now for the given plant first, we plot the Bode plot. Okay, so magnitude plot as well as the phase angle plot. Okay, so we plot magnitude and phase angle. Okay, then for this given design requirements, we will check. Okay, so from this Bode plot, will they meet these design specifications? If not, you need to reshape. You need to use the compensators and reshape these Bode plots. Is this clear idea?
Yes, sir.
Yeah. So generally in the time domain, okay, so we'll be having rise time, peak time, settling time. Okay, so they three represents the transient behavior. Okay, whereas the steady state behavior shall be represented with these velocity, position constant, velocity constant, and acceleration constant, using which we define this steady state error. Okay, so any system will have both transient as well as the steady state. So if you remember previously, the transient states maximum, what we do, so the lead compensator, okay, this will handle these transients part. The steady part done by this lag compensator. Okay, so that's what we saw. Whereas in the frequency domain, the specifications are like resonant peak, resonant frequency, bandwidth. Okay, so sometimes they are like if we have larger bandwidth, okay, so we'll have smaller time, rise time, and settling time. Okay, somehow they are all interconnected. The both time domain specifications and frequency domain specifications. Okay, so when we go to frequency domain, our design requirements will be in terms of the resonant peak, resonant frequency, and bandwidth most of the times. Okay, so this resonant peak M, okay, resonant peak is something, this one. It is somewhat similar to the maximum peak overshoot. Okay, so you have this bump here in the magnitude plot, that we call it is as a resonant peak. So if you see this resonant peak, okay, so this is mostly depends upon this zeta only. Okay, so mostly depends upon this term zeta. Okay, so the bandwidth is also closely related to zeta. Okay, so if you see the relationship between the resonant peak and the peak overshoot, okay, so somehow they are interconnected. Okay, so similarly this uh, this they're also mostly these, what we do is the specifications are in terms of these three: resonant time, resonant frequency, and bandwidth. So they will be converted into the system specifications as phase margin and gain margin, because mostly when we see this Bode plot, we deal with the phase margin, gain margin. Okay, so like the time domain specifications converted into the dominant poles, here these frequency domain specifications converted it into the requirement of the gain margin and phase margin. Is this clear? Like in the time domain, what we saw, we have this root locus. Then whether we met these specifications properly or not, we will decide based upon whether these dominant poles, how we are calculating the dominant poles. So a percentage MP is given to us and settling time are given to us. So using these two, we calculate zeta and omega n. So once we have these zeta and omega n, they are nothing but these dominant poles. Then we check whether the dominant poles are, whether your root locus is passing through these dominant poles. Now here also in the frequency domain, what we do is the specifications will be given in terms of this resonant peak, resonant frequency, and bandwidth. Those will be converted to, okay, so resonant the resonant peak, sorry, so the MR, omega R, omega B, they will be converted to this Kz and gamma, which are nothing but the gain margin and phase margin. Why we are converting these into gain margin and phase margin? Because the gain margin and phase margin directly we can see in the Bode plot. Okay, so how do we see in the Bode plot? This way. Okay, so we can clearly see here. Okay, so we can see clearly what is the gain margin, what is the phase margin at I mean what are these omega GC and omega PC also. Okay, so then we can reshape this Bode plot and check whether the gain margin and phase margin, whether they are positive or negative. Clearly we can see, like we try to see whether the root locus is passing through the dominant poles or not. Okay, so that's why we convert these frequency domain specifications into the gain margin and phase margin. Then we go for the design. Okay, so that's the major intention. Suppose here you could see, let's say for two different values of zeta. Okay, so when the design requirement changes, okay, the zeta also changes. So you see here in the phase plot. Okay, so see how this phase plot, this is how much this is above the minus 180, this much. Okay, so here this is above minus 180 of this much value. Now here you could see, okay, so that is your phase margin. Okay, so the phase margin, this first one is 0.4, let's say. Okay, so this one is 0.4, this one is 0.1. Okay, now you see phase margin with 0.1 is greater than the phase margin with 0.4. Okay, you can see the difference when you tune the design. So you will exactly see whether you are meeting the design criteria or not. Okay, So simple thing is, in the time domain given specifications, we convert them into the dominant poles and see whether the root locus is passing through them or not. There the design means you reshape the root locus plot using the compensators in such a way that the root locus should pass through the dominant poles. Here, so given the frequency domain specifications, you will check, okay, the phase margin and gain margin, and see the RC or reshape the Bode plot in such a way that you meet exact requirements of the phase margin and gain margin, which will guarantee that you will reach these frequency domain specifications. Okay, so the gain crossover frequency. Okay, so in general, the gain crossover frequency is this way. Okay, so when you substitute here, okay, so you'll get your gamma. Okay, generally larger the gamma, okay, so phase, larger the phase margin. Okay, so it is more relatively more stable. Okay, so here also you could see, okay, so based upon the type of the system, generally the relative stability of the system we comment by using these both gain margin and phase margin. Okay, as I said, steady state stability or steady state specifications will be in terms of these three: Kp, Kv, Ka. Okay, so here you could see this is type 0 system, type 1 system, type 2 system, their uh, magnitudes, how they are changing. Okay, so type 0 system, your Kp is 0 dB because it's steady state. Okay, so whereas type 1 system, you could see this is the Kv. Okay, so this is Kv. Okay, whereas type 2 system, this is Ka. Okay, so I mean these steady state specifications you can also see in the or you can use them as one of the specifications in the frequency domain. Okay, so you can check the problem statement like this. Given the open loop system, okay, J of S is equal to 4 by S into S plus 1. Okay, so you'll have both transient as well as the steady state specifications. Transient is you have peak overshoot less than 5%, 15%, settling time is 5 seconds. Okay, steady state specifications are KV is 40 seconds. Okay, so now what we do is in general, so in the frequency domain specifications, okay, so just like what we did previously, MP and TS formulas we have. Okay, so using those formulas, you can find zeta and omega n. So here you got zeta as this, omega n as this. So you can convert these zeta and omega into frequency domain specifications. Okay, so frequency domain specifications as gain margin as gamma. So gain crossover phase margin as gamma. Gain crossover frequency as this much for the given system using this formula. Okay. So now since we have not used any compensator, okay, so without compensation, okay, so you are getting phase margin as 28 and kV as 4. kV as 4. But what is your requirement? Your requirement is kV must be 40 seconds. Okay, 40 per second. The proportional, velocity constant. So the question is how to do this design. Okay, you have this K in the system. Okay, so it is like you are using the proportional controller. Only proportional controller. So whether you are keep on increasing the K, so you should see 1, 4, 10, 20. The KV is keep increasing. KV is keep increasing. So hence this phase margin is also increasing. So that you can see in the left side Bode plots. Okay. So this way you are keep on increasing the K is equal to 1 to 20. Okay. So now you could see here, so the KV increment in the similar fashion. So starting with 4, 16, 40 and 80. Okay. So for every expression, you should see for KV is equal to, sorry, K is equal to 1, first case, this case. So this is the phase margin. Okay. So now as you see, as you go on, the phase margin is getting reduced. Okay. The phase margin is getting reduced. Okay. So the gain margin is always infinity. What is the gain margin? Okay, so the gain margin at which this yeah, connects with the 0. Okay, so this one, that's always infinity. Okay, so you could change the values from 0 to infinity and see whether you met these requirements or not. Okay, so here our main intention is this one, because we want our K should be, KV should be 40, that we are getting at K is equal to 10. Okay, so now look at the another example. Okay, so in this example we have this S is equal to 0 as one pole and other two poles. Okay, similarly if you keep on increasing the gain here, K is a K from 1, 5, 10, 40. Okay, so now you could see here after some point, after this point, okay, so these two cases, okay, so your gain margin and phase margin, they became negative. Okay, till that point they are positive. Now that you can observe from here. Okay, mm. So when K is increasing from 1 to 40, okay, so the gain margin, sorry, the phase margin, okay, so that is something from 180. Okay, from 180. So these are the values initially. Okay, so 15.6 and 1.58. Okay, later you could see they are increasing, so they are becoming negative. Okay, so as the gain margin also, so gain margin initially 53, next 5.02. So 53 means what? So from here, mm, so from here you could calculate values. Okay, so from 0 how much it is deviated. Okay, so now here the point is after some value of K, the system is becoming unstable, and after K is greater than 5. Okay, because of negative phase margin and gain margin. Okay, so generally the Bode plot of any system can be divided into three categories. Okay, so can be divided into three regions. Okay, so you can see here, so in the first region, so you have this gain crossover frequency. Okay, so that will be like far below or far below or starting of the Bode plot, that we describe it is as a steady state category. So here the this one is belongs to low frequencies. Okay, low frequencies means high time. Okay, so higher time periods. Okay, next in the, that is the region 1. In the region 2 we'll have these around this gain crossover frequency. Okay, so here mostly we deal with these relative stabilities, finding these phase margin and gain margins and their variations. Okay, so we call that is also as the transient region. Okay, then so very far from the gain crossover frequency, which there we handle with the higher frequencies. Okay, so these are higher frequencies. So here mostly these are of noisy in nature. So any Bode plot of any open system will have these three regions. Okay, so in general the design procedure could be like this. What we do is we have this plant, so we have this compensator. okay, or controller. Okay, so we write this compensator as kgc dash of j omega. Okay, so then we write the overall transfer function of open loop system. So replacing gc of j omega is this. Okay, so we have two things. So gc of j omega, so k dash g of j omega. Okay, so in the first step, what we do is, so we design steady state. We design the frequency domain for the region 1. Okay, so to meet the steady state specifications. Okay, then after that, while we designing that itself, so we choose this k dash. Okay, after that we will find this g of j omega. Okay, so that is how we will go for the design. So this entire k dash g of this gc of j omega represents the compensator. Okay, so which later we will design these transient specifications. Mostly our concentration is for region 1 and region 2. You don't put concentration on noise attenuation, etc., which are belongs to the higher frequencies. Okay, so this is the idea. Okay, so maybe next live session we will go ahead with learning the lead lag and lead lag compensators, and they design just like the way we did for root locus. Okay, so mostly the both the things are comparable. Okay, so hope the idea is clear. Okay, so are there any questions in the problems I have solved and in this theory part? Because yeah, we have only 15 minutes. I'm not sure that is enough for covering the, going through the content revisit. So we can do it in next session and continue the problems.
Yes, sir. Please share
Yeah,
these notes. This.
this one, write up notes.
Yeah, yeah. The
Yes, yes.
problem that we
Yeah,
solved.
yeah. Yeah, I'll do that. I'll do that.
Yes.
Yeah. So for your problem, I have sent you an email. You are Gayatri, correct?
Yes, sir. Yes.
Yeah,
Yeah, I
yeah.
saw that.
So yeah, just check that if you can able to solve.
Ah,
So if you cannot get that, so let me know. I'll solve the entire problem and send you. Hmm?
okay. Yeah. Thank you,
Yeah,
sir.
yeah. Okay. Yeah, thanks a lot.
Yeah, thanks.